Welcome to CSC 201, Lesson 4.8, Indirect Argument, Two Famous Theorems. We want to prove that square root 2 is irrational. This is a very famous proof by contradiction. We are going to suppose not. That is, suppose square root 2 is rational. That we have a definition for. Thus, square root 2 can be rewritten as a over b for a and b elements of the integers and b not 0. Okay. Further, suppose we've chosen a and b in lowest terms. We've written a over b in lowest terms. So we've reduced that fraction, a over b, as much as possible. A and b have no common factors. So that should be possible for any rational number. If you can write it as a ratio of two integers, we can simplify that fraction and put it in lowest terms. So observe that square root 2 equals a over b tells us that if you square both sides, 2 equals a squared over b squared, which tells us that a squared equals 2b squared, which tells us that a squared is even, which by a theorem in the previous lesson that we proved tells us that a is even. That was a proof by contrapositive. So we're just going to assume that we know that now. If a is even, then a is 2 times an integer. Thus, substituting a equals 2k into this equation, 2 equals a squared over b squared, yields 2 equals 2k squared over b squared, which tells us 2b squared equals 4k squared. Okay, I just multiplied both sides by b squared, and I squared that numerator there. And thus, b squared equals 2k squared. So b must be even. B squared must be even. And hence, b is also even. Okay, so we've now reached a contradiction because we proved that a is even and b is even, but that contradicts our assumption that a over b was written in lowest terms. So here's our contradiction. If a and b are both even, then a over b is not in lowest terms. Thus, our supposition that square root 2 is rational must be false, so square root 2 must be irrational. Okay, we want to prove for any integer a and any prime number p. If p divides a, then p does not divide a plus 1. So if a prime divides an integer, it does not divide the next integer. This is a little lemma that we're going to use in the next example. The big proof we're doing right now today is that we want to prove that the set of all prime numbers is infinite. Okay, so this is a small theorem called a lemma that we're going to use in the bigger proof, in the proof of the bigger theorem. So for any integer a and any prime number p, if p divides a, then p does not divide a plus 1. We're going to do this proof by contradiction. Okay, so we're going to suppose not. So we are going to suppose the negation of this statement. So we're going to suppose that there exists an a in z. So there exists an integer a and a prime p such that p divides a and p divides a plus 1. Okay, so that is the negation. For any integer and any prime number, that becomes a there exists when you negate a for any or for every. And then the negation of an if then is the p part and not q. So the negation of p implies q is p and not q. So I have assumed p and not q. All right, so observe that p divides a means that a is p times an integer. Also, p divides a plus 1 means a plus 1 equals p times some other integer, j, for some k and j in the integers. Okay, so it's just the definition of p divides. Now we see that 1, which can be rewritten as a plus 1 minus a, which feels like a silly way to write 1, but a plus 1 and a are values that we're dealing with here. So a plus 1 minus a would give me 1, and a plus 1 is p times j, and a is p times k, and I can factor out a p, and I get j minus k. And j minus k is an integer, so this tells me that 1 can be divided by p, that 1 is a multiple of p, or that p divides 1. Okay, so let's write that out. Since j minus k is an integer, 1 is a multiple of a prime number p. Alternately, another way of saying that is p divides 1. But we have a contradiction here because the only divisors of 1 are 1 and negative 1, and primes are defined as being larger than 1. Okay, so Since p is bigger than 1, p cannot divide 1. Contradiction. Okay. So once we reach our contradiction, we've proved it. Okay, we've proved that for any integer a and any prime number p, it must be that if p divides a, then p does not divide a plus 1, the next consecutive integer. Okay, now we want to prove that the set of all prime numbers is infinite. We're going to use the lemma we just proved above at some point. But this is another famous proof by contradiction. Suppose not. Suppose the set of primes is finite. Then there must be some largest prime number. The list of all primes would be two, 3, 5, 7, 11, and then there'd be our largest one, we'll call it P. Now, let the number n, capital N, it's going to be the product of all the primes. 2 times 3 times 5 times 7 times 11 up to P. And then we're going to add 1. Okay. So it's the product of all the primes, which is definitely composite. And then we're going to add 1. Okay, so note, n is bigger than P. Right? If you multiply all the primes together, you're going to get a really big number, larger than any of its factors, and then we're adding 1 to it, so this number n is got to be bigger than the biggest prime. Okay. So if n is bigger than p, then n is not prime, because p is the biggest prime. So it's not prime, it must be composite. Okay, so if it's composite, that means it can be written as a product of primes by the fundamental theorem of arithmetic. So we should be able to find some q in the set of primes such that q divides n. So there's some q in there that divides this number, some prime number that goes into n, because n is composite, it has to be able to be written as a product of primes. But it must also be true that q divides the product of all the primes. 2 times 3 times 5 times 7 times 11 times all the way to P, right? Because Q is in that list, so Q is a, so the product of all the primes is a multiple of Q. And now we've reached a contradiction, okay? Because Q, a prime number, cannot divide an integer and that same integer plus 1, okay, which is what n is. Okay, so by the previous question, Q cannot divide 2 times 3 times 5 times 7 times 11 up to P plus 1. So that is our contradiction, because we just said that it does divide n. Okay, we said q divides n, and then we said, but q cannot divide n by the previous question. So we've reached our contradiction, and it must be that the set of prime numbers is infinite. Therefore, there are infinitely many primes.